Homework 2.2, more on functions, video 3. Homework due Friday, May 22nd, 2020 at 11:59 p.m. Equations and symmetry of graphs. Now, although this section is about functions, we're going to step back from functions briefly and talk about equations in general and try to figure out how can we determine in advance of graphing an equation whether the equation's graph will have a certain type of symmetry. Now on the board I've got 3 types of symmetries, but honestly there's an infinite number of symmetries, but we're only going to focus on these 3. The first type of symmetry is called y-axis symmetry. Y-axis symmetry is when a graph has the y-axis as a line of symmetry. So I'm going to draw a dotted line down the y-axis. And I think you know what it means to be symmetrical, or to have an axis of symmetry. Basically, the axis of symmetry serves as a mirror. In this case, the left half of the graph is a mirror image of the right half of the graph. A graph has x-axis symmetry if the x-axis serves as an axis of symmetry, meaning that the top half of the graph is a mirror image of the bottom half of the graph. Now, origin symmetry is a little different than both y-axis and x-axis symmetry. X-axis and y-axis symmetry are what are called reflection symmetries because you're reflecting this across a mirror to get the other half of it. But origin symmetry is an example of what's called a rotational symmetry, where you don't fold half of the graph to get the other or take the reflection, but rather you rotate half of the graph to get the other. For example, let's say that this is a record on a turntable and the origin is the center of the record. If I were to take the right half of this graph and rotate it 180 degrees, so do a half revolution. And I think I can actually do this if I can find a blank sheet of paper. Excuse me. If it's not a blank sheet of paper, it'll just be a sheet of paper that I'll use. Here's one. It's got some formulas on it, but let's do this. Let's say I were to draw this graph on here. Origin symmetry means when you take the right half of the graph and rotate it 180 degrees, it gives you the left side of the graph. Not drawn perfectly, but I think you get the idea. And vice versa, the left half of the graph, if you rotate it 180 degrees, will match the right half of the graph. Another way of thinking about origin symmetry is if you turn the entire picture upside down, it's still the same. So these are the 3 types of symmetries we're going to be exploring. And I'll go ahead and tell you now, as a foreshadowing a couple of videos down the road, of these 3 types of symmetries, only 2 of them could actually exist for a function. One of them, with one rare exception, can never be a symmetry that a function's graph can have. And you can kind of tell which of these is not a function if you remember the vertical line test. Using the vertical line test, which of these graphs cannot represent a function? Answer, the x-axis symmetry graph. Because the vertical line test says if you can drop a vertical line through a graph and hit it more than once, you are not a function. Well, if you have x-axis symmetry, then every point on the top has a mirror image on the bottom. So a vertical line that hits the top must also hit the bottom again. In fact, there is only one function. There's only one function that does have x-axis symmetry. I'll dangle some bonus points out there if you're watching. If you can find the one function whose graph does have x-axis symmetry, I'll give you 5 bonus points on your next test. And by the way, if you have answered the first bonus question embedded in a previous video, it was in one of the videos about, I think it was about quadratic equations, then you're excused from this bonus, unless you're just curious. So again, 5 bonus points if you can find the one function whose graph does have x-axis symmetry. I know I just said in function can't, but there is one exception, see if you can find it. Message me in Canvas and I'll let you know if you're right. Okay, so we're going to try to determine in advance of graphing an equation whether or not its graph will have one of these symmetries, which is beneficial. If I'm graphing the equation, if I'm graphing an equation and I know in advance that its graph has y-axis symmetry, I only have to graph the right side of it because I can reflect it against the left side of it. Or if I'm graphing an equation and I know in advance that its graph has x-axis symmetry, then I only have to graph the top half. Then I can take the mirror image across the x-axis to get the bottom half. Or if I know in advance that an equation's graph has origin symmetry, then I only have to graph the right half of it, then I can rotate it to get the left half of it. So knowing in advance if an equation's graph has one of these symmetries cuts the graphing time in half. So how can you tell in advance if an equation's graph will have one of these symmetries? Well, let's think about what it means to be symmetrical. For example, let's pick this point over here on the right side of this y-axis symmetry graph. And let's just generically label it x comma y, which is a good way to generically represent a point that we don't know anything else about. Well, we could argue that we know that these are both positive because we're up here in quadrant 1, but we could be down here also. If you have y-axis symmetry, then this point has a mirror image over here. What can you tell me about this point's coordinates relative to this one? Are they the same? No, because it's not the same point, it's a different point. Are the x's the same? Well, no, because one went to the right but the other went to the left. However, because of the symmetry, the distance they traveled is the same. So although they're not equal, they have to be opposites, meaning that if this point's coordinate is x, then the other point's coordinate has to be negative x. But what about the y coordinates? Well, they're both up the same amount, so the y coordinate there would be the same. So what does this mean in terms of an equation? This means if we have an ordered pair, then we get another ordered pair for free just by changing the sign of the x. So what that means in terms of an equation is the following. If you can replace x with negative x in an equation, comma, and the equation stays the same, so in other words, if sticking a negative on the x doesn't change the equation, then the equation's graph has y-axis symmetry. So this is going to morph into a test for y-axis symmetry. In the next video, I'll write those tests over here. Right now, we're developing the concept. So if we replace x with negative x, but it doesn't change the equation, and hence doesn't change the y value associated, then we have y-axis symmetry. And it's kind of the same thing over here for x-axis symmetry. Let's pick a generic point here, and let's call it x comma y. If you have x-axis symmetry, then you have a mirror image down here. Well, what do you think the coordinates of that point would be relative to this one? Would they have the same x-coordinate? Yes, because they're both over the same amount. But would they have the same y-coordinate? No. One goes up, the other goes down, but the distance they travel is the same because of the symmetry. So if this point is up y, then this one is down y, and we can write negative y. So what this says is it doesn't matter if the y is positive or negative, we should get the same x value. So we could write a long sentence like that, but I think I'm going to write it a little bit more brief. Let's see, if you change y to negative y and get the same equation, if you change y to negative y and get the same equation, then you have x-axis symmetry. I'll show you what I mean by changing y to negative y in the next video. Well, what about origin symmetry? For example, let's pick this point up here at the top, and let's just call it generically x comma y. Where would its image be after I rotate this graph 180 degrees? It would be down here. So what can we say about this point's coordinates relative to this one? Well, if this one is over x and up y, those distances are preserved, but now they're going in opposite directions. This is back x and down y. But because it's back x, it's negative x, and because it's down y, it's negative y. So both coordinates change signs. So the test that we're going to use is if we change x to negative x and y to negative y and get the same equation, then the conclusion is that there is origin symmetry. So in the next video, we're going to actually look at equations and answer, do you have y-axis symmetry, do you have x-axis symmetry, or do you have origin symmetry, by replacing one or both letters with their opposites and seeing if we get the same equation back. One gimmick to remember: when it's x versus y, it's the opposite variable sign that you change. For example, if I change the sign on the x, I'm checking for y-axis symmetry. But if I change the sign on the y, I'm checking for x-axis symmetry. For origin, you change both. All right, we'll take a look in the next video on how to actually implement this, but this is the concept. This is the theory behind what's about to happen.